Bismillah ar-Rahman Rahim. So today we would be discussing a number of topics, and the topics that we would be discussing are introduction of stress, that is what is stress, normal stress, shear stress, and we would also discuss strain, that is normal strain and shear strain. We will also discuss the different types of loadings to which the material or the member or mechanical components are subjected. Those types of loadings are tensile load, compressive load, shear load, torque. So let's say that if we have a body which is made of some material and that is subjected to external loading. So let's consider an arbitrary shaped object which is subjected by a number of external loading. So what we are expecting when we subject a material to external loading. So the things which comes in our mind that because of the external loading, what would happen to the shape of the object or dimensions of the object. We could easily imagine or visualize that the dimensions of the material would change, it would change, which means that deformation would occur. And secondly, as the material is not, because of the application of the load, if the material is not disintegrating into fragments or it is not breaking or failing, so it means that the material is actually resisting the external loading. So we could easily say that actually when an external load is applied on the material, then these two things would happen. Deformation would occur in the material, that is actually the dimensions of the material would change. And for the deformation of the material, we come up with the concept, and that concept is strain. Strain is actually the change in dimension per unit dimension. This is the definition which we normally have for the strain. Change in dimension per unit original dimension. And also we discussed that the second thing that would happen to the material if it is not disintegrating into fragments because of the application of the load, the material is resisting the external load, so the resistance of the material is there for the external load. And in order to clear the concept of the resistance of the external load, internal resistance of the material to the external load, we come up with the concept of stress. So actually, why we are defining strain and stress? Last time we discussed that we are interested um in the in that if a material, when the material is subjected to external loading, so what happens to the material? What would be the behavior of the material? And we want to study the behavior of the material. And in order to study the behavior of the material when it is subjected to external loading, we come up with the concept of this stress and strain. With strain is related to deformation, which would occur as a result of the external load, and stress would be related to the internal resistance of the material as a result of the externally applied load. So question comes that from where this internal resistance comes in the material. As we know that the material is made of atoms or molecules, and these atoms or molecules are actually connected or attached to each others with bonds with bonds. And when we subject the material, the object which is made of the material, to external loading, so actually the atoms or molecules, because of the external loads, they move relative to each other. They move relative to each other. And because of that relative motion, we have deformation, change in dimension. And also because of these bonds are actually taking the external loads and they are not allowing the atoms or molecules to detach from each other. So the material is not disintegrating. So the internal resistance is coming from those interatomic or intermolecular bonds. So that resistance is a real phenomena. It is a real phenomena. The resistance comes from the bonds which are actually attaching the atoms and molecules within the material. So in order to study that resistance, internal resistance of the object, we come up with the concept of stress. And in order to study the change in dimension, that is deformation in the material, we come up with the strains. So both are actually physical phenomena. Both are physical phenomena. So stress. Now we would define the stress. Um, Stress is actually the internal resistance of the material against the external loading. And normally, if we classify the stress, we could classify the stress into normal stress and shear stress. Normal stress, we are discussing this here. Things would be more clear as we go over more slides and we study the stress and strain in more detail. So in normal stress, the definition of the normal stress is that if a load or force is actually perpendicular to the area, this is the area, cross section area, this is the cross section area of the material. If the external load is perpendicular to the cross-section area of the material, then this is the mathematical model. We will discuss this model in the coming slides. Sigma stands for normal stress, and the mathematical model for normal stress is load per unit resisting area. So P by A. So whenever the load is perpendicular to the resisting area, then the stress that is produced as a result of that type of loading, we would classify this as normal stress. So here you could see that the load P is perpendicular to the cross-section area A. So if that is the case, we would term this as a normal stress. Another case, this is let's say the same cross-section area, but here you could see that the load is acting along the area. It is along the area. It is parallel to the area. So in that case, we classify this as shear stress. This is the resisting area and the load is along that area. It is not perpendicular. And shear stress, we would denote shear stress by the Greek letter tau. And in this case, tau is equal to shearing stress by shearing area. Shearing load by shearing area. Here the shearing load is P and the shearing area is A. Uh, Here you could see that the load is parallel to the resisting area. So one stress, we would have normal stress, we would have shear stress. You have to just look at the loading and the orientation of the area. If the load is perpendicular to the resisting area, cross-section area, then that would be a normal stress. And if the load is parallel or along the area, then we would classify or you have to term that as shear stress. Strain, the definition of the strain is the change in dimension per unit original dimension. Change in dimension per unit original dimension. Again, we would have normal strain and we would have shear strain. Let's say if we have a rod, this is a rod, and we are subjecting the rod to a pulling force. We are exerting one load in that direction and the other load in that direction. we are applying a tensile load. So as a result of what would happen, the length of the rod, which is actually L, it would increase. And let's say that increase in length is delta, that increase in length is delta, then the normal strain, because here this is actually the resisting area, and the load is perpendicular to the resisting area. So in that case, we would have normal strain, and normal strain is denoted by epsilon, and epsilon would be equal to plus sign stands for elongation. Elongation. If there is increase in length, you have to put plus sign, which would represent elongation. If there is decrease in length or shortening, then in that case we have to put negative sign, which would mean shortening. And the change in dimension is delta divided by the original dimension, and the original dimension is L. So in this case, the normal strain epsilon is equal to plus delta by L. Shear strain, for the shear strain, let's assume that we have a material. This end of the material is, let's say, it is fixed, and we are applying a load on the top of the material here, and because of which the material would bend like this. This would be the new shape of the material because of the application of the load on the top surface of the material. This dotted line would show the new shape of the material. And let's say this point moves from here to here, and this distance is delta. The angle traced by this end is, let's say, lambda. It is lambda. So normally shear strain, this is actually the shear strain. Lambda we term as a shear strain. So lambda mathematically would be equal to, this end is actually, let's say, this height of the material is L. So in this right angle triangle, tangent gamma would be equal to perpendicular, which is delta, divided by the base, which is L. So tangent gamma is equal to delta by L, and we are expecting small angular deformation, that is angular deformation. So if this angle is small, then tangent gamma would be approximately equal to gamma. So shear strain, which is gamma, which is the angular deformation also, gamma is equal to delta by L. So this is the mathematical model for the shear strain. This is the mathematical model for the normal strain. So we would have stress, and we would have strain. We would have normal stress, we would have shear stress, we would have normal strain, and as well as we would have shear strain. Now comes to the introduction of types of loading. So if we have a material, let's say if we have a rod and we are subjecting the rod to the pulling loads, we are applying one load on this end and the other in the downward direction. This end, this type of loading is tensile loading. This is the pulling loading. As a result of which, what would happen? The material would elongate. The rod would elongate. The length of the material would increase. It would increase. So such type of loading is known as tensile loading. Here we have the same rod, however, it is subjected to a pushing load. We are pushing this end and also this end. This type of loading is known as compressive loading. As a result of which, what would happen? We would have the material would squeeze. The length of the material would decrease, shortening would occur. We have the same material, same rod, but now we are applying one load on this face, we are applying a load in that direction, and on the other opposite face, we are applying the load in the opposite direction. Now the resisting area, this is the resisting area. Here, this is the resisting area, this is the resisting area. If you look here, the resisting area, the load is actually perpendicular to the resisting area. So in this case, we have what we have. normal tensile stress. Here the resisting area, this area is actually resisting the load. So again the load is perpendicular to the resisting area. So we have a normal stress and strain. Here, here actually if you look, the resisting area is this. So it is parallel to the resisting area. So this is the case of shear stress, and the loading is actually shear loading. It is shear loading. Again, we have the same material. Let's say we have fixed, this end of the material is fixed. This is the symbol for fixed end, and we are applying a moment or torque about this axis, the dotted axis. We are applying a torque, so the material would twist. Such type of loading is known as torque. Again, we have the same material, but this end of the material is fixed, and we are applying a bending moment about this point. This point we are applying a moment. So this would bend. This would bend. This type of loading is known as bending loading. So in this course, we would discuss all these different types of loading: tensile loading, compressive loading, shear loading, torque, and also bending loading. Actually, why we are coming with the concept of stress, as we just discussed that when we subject a material to the external loading, then two things would happen: deformation would occur, and also, since the material is not disintegrating so easily, we could say that the material is resisting the external loading, and that resisting internal resistance is actually coming from the bondings of the materials. So actually, when we are talking about the stress, we you have to imagine that we are talking about the internal resistance which is coming from inside the material as a result of resisting the external loading. So you have to visualize all these things, and in order to visualize this, we have this slide. So here you could see that we have, let's say, a rod, and we are subjecting a rod to a tensile loading. We are pulling this end and also this end. So when tensile loading F is applied to the material, here we have a axial loading. Axial loading means that the load is along the axis of the material. So if we have this rod, this is the axis of the material. If the load is along the axis of the material, such type of loading is known as axial loading. Uniaxial loading, uniaxial loading means that the load is along one axis of the material. In Cartesian coordinate, we would have three axes. We would have three axes. Let's say this is x-axis, so this would be a y-axis, and then we would have z-axis. So you could see that the loading is along one axis only. So such type of loading is known as uniaxial loading. So initially, for simplicity, we would consider only uniaxial loading. Then afterward, when the concept is clear to you, then we would be considering biaxial loading and also triaxial loading. So now we are subjecting the material to the tensile loading, and as a result of this tensile loading, what would happen to the length of the material? Obviously, the length of the material would increase, the material would elongate, and the resistance, this is actually the area, this is the resisting area which you could see as A. So the resistance is coming from all these material or this area. We could say that this is the resisting area. So in order to see the internal resistance, actually what we are doing, we have to visualize. Actually, in reality, it is difficult to measure the internal resistance because it is in order to measure the internal resistance of the material, that is the uh, resistance coming from the bars of the material, it is not easy, or even it is impossible to measure that internal resistance, because for that you have to go inside the material, you have to cut the material, you have to put sensors in the materials, huh? So you're damaging the material. So actually this is not the way we engineers have to proceed the problem. We have to use another tool, and that tool is visualization, imagination. So what I'm doing, what we would be doing, we have to imagine. And as we are here, we are imagining that if we subject a material, this material, to tensile loading, the material would expand. Similarly, the resistance would be coming from this area. If we cut this into two pieces, if I take a cutting plane at this point and I cut this into two pieces, as you are seeing here, and now I'm making the free body diagram of each segment. So this is the top segment and this is the bottom segment of the rod. So if the component is in equilibrium, then it's each and every segment should also be in equilibrium if we are drawing the free body diagram. So here you could see that we have this force which is acting on the top of the top end of the rod. So here you see that force here. In order to make an equilibrium, in order to make this segment in equilibrium, actually we have to apply a load in the downward direction. And let's say that load would be the same, otherwise it would be not in equilibrium. So the magnitude of that would be F. Similarly, in order to make the bottom segment in equilibrium, here you see that this load is acting in the downward direction. So we have to apply another load which would be acting in the upward direction, and the magnitude would be the same F. So here we would have force F. The magnitude of the force would be F. And from where this force is coming? From where this force is coming? This force is actually representing the internal resistance which is offered by the material, by the bondings of the material. So let's say it is R. Internal resistance is R, and internal resistance is actually equal to F. So we could easily visualize that there would be internal resistance, and that internal resistance would be coming from the material, from the bonding of the material, and let's say that internal resistance is R, but that internal resistance would be equal to the external load, because our actual system is in equilibrium. So each and every segment, it's each and every particle would be in equilibrium. So here this is the area, this is the area. If you look here, this is the area, cross section area, this is the cross section area of the material, and this is A. Normally the internal resistance which is coming from the material, it would be not uniform. More resistance would be from the particles which are at the center, and less resistance, relatively less resistance from would be from the particles which are at the surface, which are at that surface. So meaning that at the, if we have a load distribution in the middle, we would, the load would be the resistance would be high. However, at the side the resistance will be relatively less. However, here you see that the stress distribution over the surface. Here we are showing the stress distribution of the stress distribution over the surface. Sigma. Sigma stands for normal stress. Here you could see that this force is perpendicular to this area. So the concept that we would be using here for the stress is the normal stress. So here we would be using the terminology of a normal stress because the load is perpendicular to the area. So sigma. And the stress distribution, you could see that it is uniform. Again, this is an assumption. We have taken an average. an average or uniform distribution over the cross section area. And why we are doing that, we would discuss this on the coming slide. So here we have the same rod, and we are subjecting the same rod to the tensile loading or pulling loading, and I'm taking this section. This is section MM, section MM. So if we take section, I'm taking section MM, and I'm taking the below segment, this segment. If we cut this into two parts, and I'm taking the below segment of the material, so you could see this force here. This is the force which is acting on the bottom face of the material. On the other end, we would have the stress. We would have the reaction force, the internal resistance, but I'm not showing the load here. We are showing the stress distribution. So here you could see that the stress distribution is actually maximum at the along the axis. Along the axis, it is maximum, and near the surface, the stress distribution is relatively less or small. The reason is that here, if you consider the material, on both sides of the material, we have again the materials are bonding. So more of the resistance we are expecting from the particles or atoms or molecules at the center. Here, if you consider these particles or these bonds, there is nothing here. There is nothing here. So actually, we are expecting that less resistance would be coming from the particles or bonds which are available at this surface. So the stress distribution, we are expecting that the stress distribution would be like that, which is in reality non-uniform. Similarly, here, if you take this section, and if I show this segment here, this is the force which is acting in the downward direction, and in order to have this in equilibrium, we have to show either the resistance force here or the stress. So here we are just showing the stress, normal stress distribution, and again you could see that the stress is maximum at the center. However, at the faces, it is relatively small. So if we want to find the let's say uh, s- let's say I'm taking a small area. I'm taking a small area on this uh, face of the material. I'm taking small area dA, and then we have to apply the mathematics, and we have to come up with the mathematical model for our stress. So I'm taking a small area here. This, let's say this whole area, you are seeing the one dimension, two dimension, one dimension shape, but assume that we are taking a small area here of the resisting area is A. I'm taking a small area dA, and on this small area dA, the resistance force which is coming from that small area dA, it would be dr. Dr is the small resistance, internal resistance, which is coming from this small area dA, and and over that area, let's say the stress, normal stress is sigma. So dr, we could write down dr is equal to sigma dA. And in order to find out the internal resistance for the whole area, in mathematics you have learned that we have to integrate. So integrating on both sides of this mathematical equation. So if we integrate here, so this integral and differential sign would cancel with each other, and we would have R. R is the internal resistance on this side of the material, and we would have integral sigma dA. Now, because here sigma is actually not uniform, So it is not possible, it is not easy to actually integrate if this is a variable or it is not uniform. So it is not mathematically easy to solve this integral. So what technique we are using? We are using the averaging technique, which is a valid technique, which gives us an approximate solution. So what I am doing, we are taking uniform distribution of stress, and that uniform distribution would be the average normal stress. So we are taking, instead of this small uniform um, stress distribution, we are considering average distribution over this cross section. So sigma average, which is uniform. So what I'm writing here, I'm taking this as sigma average. So sigma average integral sigma average dA. Now if you look here, sigma average is uniform. We have taken this or assumed as uniform over the surface, which would give us an approximate solution. So if sigma average is uniform, so we could take this sign of integration. So it is equal to sigma average integral dA. And integral dA is what? Integral dA would give us the whole area, cross section area or resisting area. So from here we would have sigma average A. So now our equation would become the internal resistance R, which is actually equal to F, because our this segment is in equilibrium. Our actual system is in equilibrium, so this segment should also be in equilibrium. So the internal resistance R is actually equal to the external load F, and it is equal to sigma average times A. And from there, the average normal stress is equal to F by A. F by A. So this is the mathematical model for the normal stress, where F is the external load and A is the resisting area or the cross section area of the material. So actually here we have R, the internal resistance. But as we discussed that actually it is not easy to measure the internal resistance, which is coming as a result of the external load. But here we could easily see that the internal resistance is actually equal to external load, and it is easy to actually measure the external loading. Here we are applying the external loading, and it is very easy to measure this external loading. We have sensors, we have load sensors with which we could actually very easily find the external loading to which the material is subjected. So our mathematical model would become sigma average is equal to F by A. So many students, when we ask that define stress, they say that load per unit area. It is not the definition of the stress. It is just the mathematical model which we are using to calculate the stress. The definition of the stress is the internal resistance of the material against the externally applied load. That is actually the definition of the stress. Also remember that as we are saying that it is actually not possible to measure the internal resistance of the material when the material is subjected to external loading. So actually it is also not possible to measure the stress. We are not actually measuring the stress. Stress is such a phenomena which we cannot measure. It is not a parameter like pressure, force, acceleration, velocity, mass, weight, which we could measure. It is not measurable quantity. Rather than we calculate the stress. It is not a sensible quantity. We could only calculate the stress with mathematical models. As you see here, we could find out the average normal stress in that case with this mathematical model. This is just a mathematical model for finding the normal stress in case of tensile loading. So further talking or discussion about the tensile loading. So let's say we have a rod and we are subjecting the rod to tensile loading or pulling loading. So tensile loading, axial loading, you could see that the loading is along the axis of the rod. So it is axial loading. The loading is along one axis. It is not along two axes or three axes. So we have the case of uniaxial loading, tensile loading. And what we are doing, I'm passing a cutting plane. Let's say I'm taking this cutting plane and I'm cutting the rod into two pieces. So this is the top portion and this is the bottom portion. Here you could see this load here and you could see this load here. If the rod is in equilibrium, then our each and every segment should also be in equilibrium. Then it would be the complete freeboard diagram. So if we have a load here in that direction, then we would have a load. I have to apply a load in the downward direction in order to make this in equilibrium. Similarly, if on this face we have a load in the downward direction, so on this face we have a load in the upward direction, and this would be the internal resistance which would be coming from the material at that section, at that particular section. This would be the internal resistance R, and it must be equal to P because our system is in equilibrium. So each and every segment should be in equilibrium. And if we have a round rod, then the cross section area here would be pi d square by 4. This is the mathematical model for the round area. So we have a tensile load, as a result of which we would have a tensile stress, which is actually a normal stress, because here this is the area, resisting area, and the load is perpendicular to that area. So we have a normal stress. So stress is a normal stress. So we have to denote this by sigma. This sigma, we are not writing the average here, because now we understand that this mathematical model, that is P by A, is actually would give us the average stress. So sigma is equal to the internal resistance, which is R, per unit resisting area, which is A. Internal resistance we could relate very easily to the external loading. So R by A is equal to P by A. So here the tensile stress, which is a normal stress, the mathematical model would be P by A. So with this mathematical model, we could very easily find out the normal stress at this particular section. What we need for that? We need the external load. So you have to measure the external load, or you must know the external load. And we need the area, the resisting area or the cross section area. So if you know the diameter of the rod, then with this mathematical model, we could calculate the area. Capital A is equal to pi d square by 4. So after putting those values, we would get the normal stress. For tensile stress, we have to use the positive sign. And for the compressive stress, we have to use the negative sign. So here the stress would be plus P by A. The unit in SI system, the unit for a load or force is Newton, and the unit for area is meter square. So the unit for stress here would be Newton per meter square. Again here, when we subject this rod to the tensile loading, what would happen? The length of the material would increase. And let's say delta is the deformation or increase in length of the material, then the normal strain here, as the load is perpendicular to the area, so we would have a normal strain, and that normal strain, that is epsilon, would be equal to plus sign for elongation, because here we are expecting that the material would elongate. So plus delta. Delta is the deformation, that is change in dimension per unit original dimension, and the original dimension, let's say the length of the rod is L, so divide by L. Plus sign shows elongation. The unit here, it is length deformation or change in length. We have to measure in units of length, and original length is also the unit of length, so it is just a ratio. So it is unitless. Or also sometimes we write inch by inch or meter by meter. So we could write those with the strain. Why we are writing inch by inch or meter by meter? In order to understand when we are doing calculation, so it must be because we would be using other ratios such as Poisson ratio, or dilatation, etc. So in order to clarify that what I am writing, it is a strain, so we have to write down the unit inch by inch or meter by meter with that. Now another case, we have the same rod, but we are applying the pushing load here, and that pushing load is along the axis. So, and there is only one load, and the load is along one axis. So again we have a uniaxial loading. The loading is compressive loading. It is compressive loading. Because of the loading, what would happen to the length of the rod? It would decrease. It would decrease. And again, I am taking that section here. I am dividing this into two portions. And here you could see that the internal resistance is coming at this section. It is coming from this area. And that internal resistance is actually equal to the external load. So we have a compressive load, uniaxial load. A result of the compressive load, we would have compressive stress. The load is actually perpendicular to the cross section area. So again, we have a normal stress. So sigma compressive is equal to minus sign for the compressive stress. For tensile stress, we have to use positive sign. For compressive stress, we have to use negative sign. So the average compressive stress would be equal to minus the resisting force, which is coming from the material, R, divided by the area, and this R is equal to P, so is equal to minus P by A. So compressive, the mathematical model for the this compressive stress would be minus P by A. And the strain is equal to minus sign for the because we are expecting here that the material would shorten, so negative sign for shortening, and the deformation is, let's say, delta, so delta divided by the original length L, and this negative sign shows compression or reduction in length. Now we have the same rod, but now we are applying this to a load one, and the load is not along the axis. It is not acting along the axis of the material. This is the axis of the rod. On this edge, we are applying a load in the downward direction, and on this edge, we are applying the load in the upward direction. Same rod, but now we are expecting that if the material fails, it would fail along the height. It will fail along the height. In other cases, the material would have, if the material would fail in that case, in the tensile loading, it would be along this area. It would be along this area. But in this case, we are expecting that if the material breaks, it would break along the uh, height or length of the material. And here I have shown the two, if in case it fails, the two portions of the material. But what does it mean? It means that the resistance is actually coming from this area of the rod, not from the area which we have discussed in case of the compression and tensile loading. So here this is the resisting area. And if this is the resisting area, you could very easily see that the load is actually parallel. This load or this load is actually parallel to the resisting area. So again, if the load is parallel to the resisting area, then in that case we would have shear stress. Such type of load is known as shear load. It is shear load. This is actually the shear load here. This is shear loading. So we have a shear loading, and a result of this shear loading we would have shear stress. And shear stress is denoted by tau, and it mathematically it would be shearing load by shearing area. Here the shearing load is P and the shearing area is this. This is the resisting area, shearing area, and we have to calculate this shearing area. If we look to this area, if I look to this portion in that direction, you would just see a rectangle. So here the resisting area is in the form of rectangle. The diameter of the rod is D. This dimension is D, and L is the length of the rod. So here the resisting area, the shearing area is length times diameter. So you have to know the load, shearing load, and you have to calculate the shearing area in order to have the shear stress. Some more discussion about the stress. Question normally arises whether stress is a vector or a scalar. For those quantities which need magnitude as well as direction, we term them as vectors. And those quantities which only need magnitude but direction is not necessary, we classify them as scalars. For example, velocity is a vector. Uh, speed is a scalar. Displacement, distance is a scalar. Displacement is a vector. Acceleration is a vector. Mass is a scalar. So in order to simplify the things for ourselves, we come up with the concept of scalar and vector. We know that in three-dimensional space, in Cartesian coordinates, vector has three components. One component along x-axis, one along y-axis, and the other along z-axis. So vectors have three components. stress stress is actually neither a scalar quantity nor a vector quantity. We use another actually term for it, which is actually new for you guys, and it is tensor. Stress is actually a tensor. Stress has 9 components, and normally we write all those 9 components in a matrix form. So stress would have these 9 components, which we have to write in the matrix form. Sigma x-axis, sigma xx, tau xy, tau xz, tau yx, sigma yy, tau yz, tau zx, tau zy, sigma zz. So here you see we are using two subscripts. Sigma xx, the first subscript would show you the direction of normal of area. The first subscript, what the first subscript would show? It would show you the direction of normal to the area. So we would have an area, and normal to the area, the direction of that normal would be the first subscript, and the second subscript would show you the direction of force. It would show you the direction of force. And also here you see that sigma is normal stress. So along the diagonal, you could see that along the diagonal we have normal stress, and all the remaining components are tau. So all the remaining components are shear components or shear components. So up till here, things must be clear to you. So with this, I am finishing this discussion.